Recording in progress.
Hello, my name is Jacqueline McLaughlin. I'm currently a rising senior at Drexel University. I work in Dr. Palmisi's Polymers and Composites lab. And today I wanted to present my undergraduate research on a two-component resin formulation for DLP 3D printing and studying the influence of reactive diluent on vinyl ester properties. So to begin with a brief overview of additive manufacturing, this is commonly referred to as 3D printing. And these fabrication techniques construct parts in a layer by layer fashion. This serves to limit material waste and enhances product design capabilities without changing of large or expensive tooling, as is often the case in subtractive or formative conventional manufacturing methods. So polymeric materials do constitute the largest class of materials that are currently used by a variety of additive manufacturing fabrication techniques. This is shown here in this pie chart that's provided by the National Institute of Science and Technology in their report on additive manufacturing materials. So on the other side of this slide here, I show an array of available polymer additive manufacturing techniques. These are very specific to the type of polymer that is being processed. For example, thermoplastics often require melt and extrusion type methods, including fused deposition molding and fused filament fabrication. However, the parts produced by these methods are often anisotropic and they're pretty relatively weak. So they're not really great for end use or structural applications. However, thermosetting materials that begin as photopolymer liquid resins are often generated by UV-based methods or light-based methods, such as stereolithography shown here, or digital light processing shown here. Since these thermosetting materials form a cross-linked polymer system, chemical bonds can form both within printed layers and then between printed layers. So this serves to reduce the overall anisotropy of these printed parts and also enhances their thermal mechanical properties as well, making them much more advantageous for end-use products and structural applications, high-performance applications, things of that nature. One of the most commonly used fabrication techniques within additive manufacturing for thermosets is digital light processing, and I use this in my work as well. So in a very general sense, how this operates is that the build platform lowers into the vat of resin. Light is shown onto the vat of resin in a specific geometry depending on the shape of the printed layer that's being formed. This causes the resin to cure or solidify onto the build platform. It adheres to it, and after a certain amount of time, which is predetermined by the user, build platform lifts with the part adhered to it. And this process continues over and over again until the entire part has been created. So these technologies offer wide range of available systems, and you can get good design resolutions in your printed parts, and there's an ability to create complex internal structures as well. However, there is a limitation on the build materials that are currently available, especially commercially, and printed parts generated by DLP often require a post-curing material in order to get them to their highest structural, mechanical, and thermal properties that they can attain. So you can't just use them right out of the printer, which is a pretty big drawback for these. So we take a look at some of what has been reported in commercial resins. I've collected the data here, presenting them sort of like a scatter plot. We can see that a lot of these systems don't attain really high don't attain very high tensile strengths. Much of them remain below 60 megapascals. However, they can attain high thermal properties owing to the high cross-link density of these networks. So with this combination of properties, one, they're not very strong at all. And because the high cross-link density of these networks do occur within these printed resins, they're also pretty brittle. So really the only thing you're getting here are some decent thermal properties, and they're not much good for real life applications where you might need something a little more durable and able to handle a certain amount of load. The most common photopolymerizable functional groups that are used in these resins that I'm showing here include acrylate, methacrylate, and epoxy resins. Even though epoxy resins are very well known and well established for their high performance capabilities, these systems do tend to have higher viscosities than methacrylate and acrylate-based systems. They also cure a lot slower, so they're not as amenable to additive manufacturing techniques as acrylate-based systems are. Vinyl ester resins are known to impart high thermal properties, mechanical integrity, and chemical resistance to both thermosets, and when they're used in polymer matrix composites as well. These materials are formed from bisphenol A epoxy-based resins using methacrylic acid, and the two aromatic rings in the center here give these materials their higher stiffness and strength than your normal linear polymers would. And then the two terminal methacrylate functionalities there give the photopolymerizable capabilities to these systems. They cure by free radical mechanism, so they cure much more quickly than an epoxy resin would. They're already used in a wide array of applications, as I have listed here. So it's interesting to consider these materials to improve the overall properties of additively manufactured thermosets. These viscous materials, when used on their own, are very, very difficult to work with. So they do require a diluent of some sort, and the most common diluent is styrene. Styrene is added oftentimes as a reactive diluent. It very effectively reduces resin viscosity and enhances the degree of overall cure as well, so it is able to improve the performance of vinyl ester-based materials. Unfortunately, styrene is very volatile. It is carcinogenic. It is a hazardous air pollutant, volatile organic compound. So we don't necessarily want this in additive manufacturing resins, since there is such close proximity between users and the manufacturing technology itself. So we definitely want to eliminate this from the system, consider alternatives. There are two main classes of reactive diluents that are used in vinyl ester systems. Methacrylate reactive diluents are often used in dental applications. These systems do achieve high degrees of double bond conversions, but they do have slower reaction rates. And the methacrylate functionality on everything within the system prohibits comprehensive study of network formation by spectroscopy techniques. So one is not able to draw very good structure property relationships within these sorts of systems. On the other hand, we have vinyl reactive diluents. So these are often used in fiber reinforced composites. They produce thermosets with better properties relative to those using methacrylate reactive diluents. They allow for faster reaction rates, and the distinct vinyl functionality here allows for the study of copolymerization reactive pathways and drawing those structure property relationships as well. So these three monomers that I have listed here, paramethylstyrene and vinyl pyrrolidone and 4-acrylmorpholin, have been used to a very small extent in methacrylate resins, but they haven't been explored very much in detail, nor have they been explored within vinyl ester systems. So they are going to be under consideration in this work for the formulation of a vinyl ester-based resin that's intended for DLP. And we want that to exhibit improved properties relative to available photopolymerizable thermosetting resins. To begin this process, I look at material selection. Why are we choosing these materials? And resin processability, determining whether or not these diluents make processable systems before even printing anything and testing it. Following this, we study the copolymerization reaction kinetics and determining how the copolymer network is formed between these two components and what the composition of that is, what it might look like. And then finally, an evaluation of thermal and mechanical properties will be conducted using various techniques that I'll talk about throughout this presentation. So again, to begin looking at the properties of these chemicals themselves, the three alternative reactive diluents have slightly higher molecular weights and viscosity than styrene does. Relatively though, they are still smaller molecules, but what really makes these chemicals of interest specifically are their vapor pressures. Take a look at this last column here. They are much lower in vapor pressure at room temperature than styrene is. Because styrene is such a high vapor pressure, it's much more easier for it to be given off, release those very dangerous emissions, and that is what we want to avoid. So having a lower vapor pressure is very ideal for these systems. So because of what we know about styrene, it is not something that I've printed with. I compare it to some thermally cured systems that have been reported in the literature, but it's a little dangerous to print with. These other three diluents I've combined individually in vinyl ester resins in the amount of 35 weight percent in order to determine their processability, their copolymerization behaviors, and their thermomechanical properties as well. In order to determine their processabilities, there are two important things to consider. That is, one, their printing parameters, and two, their viscosities. So looking at this working curve analysis on the top here, we can see from the slopes of these curves that they do differ very slightly depending on the chemical composition, but not too significantly. What's important to take away from this is that these resins can be printed, and that's important to determine. And the other parameters that you can calculate from these curves allow you to determine a proper printing schedule in order to print successful parts. Following this, looking at resin viscosity, like most polymer processing techniques, additive manufacturing processes, like digital light processing, have a viscosity threshold. For DLP, that threshold is around 5,000 centipoise. It's also often desirable to have a resin that's lower in viscosity, below 1,000 or 500 centipoise, to give you better design resolution. From this data here, we see that paramethylstyrene gives us the lowest viscosity resin at this concentration of diluent, and acrylomorpholin gives us a much higher viscosity at this concentration of reactive diluent, owing to the higher viscosity, molecular weight, and polarity of these monomers. But the main conclusion here is that although processability varies slightly by the reactive diluent that you use, all of these resins are processable by DLP and can be printed. So following this, I took a look at the reactive kinetics and copolymerization cure kinetics of all of these systems, again with 35 weight percent of each respective diluent. These lines here do follow the general trends of free radical polymerization. However, just based on looking at the curves themselves, even without knowing anything else, you see that there are differences according to the chemistry within the systems. These open markers are indicative or representing the reactive diluents, and then the closed markers are representing the vinyl ester oligomers themselves within each system. So to begin, before any reaction occurs, there's an oxygen inhibition period, and we can see here that this time varies slightly for each of our resin systems, being the shortest for when NVP is used, moderate for acrylomorpholin, and a little bit longer for paramethylstyrene. Following this, there's an autocatalytic region of propagation. Within this region, a majority of the polymer network is formed, and from the slopes of these curves, we can get an idea of what the rate of polymerization is. Based on this information here, the curves of acrylomorpholin in vinyl ester and paramethylstyrene in vinyl ester within those two systems show pretty good overlapping of both monomers, which indicates that copolymerization is happening. However, for the NVP in orange here, that is certainly not happening. And there is something else which is occurring, which we can kind of uncover a little more using reactivity ratios and come to a more conclusive argument on the following slide. But to round this out, I do quantify the rate of propagation according to these slopes as well, to better show how they're correlating, as I've just discussed. And then finally, we have diffusion limited propagation. So after a sufficient amount of the network is formed, the viscosity of the system increases, making it harder for components to move around and react. And this is why a lot of printed parts require post-curing to increase the final conversion past the diffusion limited region that we see here. So calculating reactivity ratios from what we just saw, again, will give us some more conclusive evidence as to the exact polymer network that is forming, telling us the composition and the structure to enable structure property relationships to be drawn. So during free radical polymerization, a few events can occur. The first of which is that when a vinyl ester oligomer perhaps becomes reactive, it receives a free radical. It can transfer this radical to another vinyl ester oligomer, or it can transfer it to a reactive diluent monomer. Likewise, if a reactive diluent monomer becomes active, It can transfer this radical to another diluent monomer or a vinyl ester oligomer. It just depends on which is more reactive with which, and that can depend on the chemistry of the system. So using this equation here that's been established in the literature, we know the relative concentration of both resin components. We know from the previous experiments the rate of reaction, and by plugging in arbitrary values for R1, we can determine the reactivity ratios for the two components within each system. This has been reported and pretty well established for vinyl ester and styrene as well. So I've reported those here to see how similar or different we are from that traditional system. When R is greater than 1, it indicates that a component prefers its own radical. When R is less than 1, this indicates that a component prefers to transfer its radical to the radical of the other monomer. And then if R is around 1, then either scenario is equally likely. And if we just take a look at these systems here, we see that all the numbers are very different. So when a polymer network forms, each of these black chains can look a little different. And again, that depends on the reactivity ratios and the curing kinetics that I've been discussing so far. For paramethylstyrene, when that's used within the system, we see that vinyl ester monomers like to transfer radicals to other vinyl ester monomers, and paramethylstyrene prefers the radical of vinyl ester monomers as well. So this likely creates a random copolymer network, as is the case with styrene. NVP shows us a very different story. Vinyl ester monomers do not want to react very much with NVP monomers at all. And NVP monomers may want to transfer some radicals to vinyl ester monomers. This is a very small number. So it is also likely that it could be homopolymerizing as well. So this creates a block copolymer in which you have large blocks of vinyl ester and maybe some small NVP incorporated or dispersed throughout there. Finally, in vinyl ester and acrylomorpholin systems, both reactivity ratios are below 1. So each component prefers the radical of the other, and this forms a nice alternating copolymer network. Based on this information, it is very clear that the copolymer that forms is very different depending on the diluent that you use. So a question that is very apparent here is, what bearing does this have on the properties of the overall polymer network? So first, we can look at thermal properties. I ran some dynamic mechanical analysis, or DMA, experiments, and I show as printed as well as post-cured samples that I've run on those. And I provide the fractional conversion for all of these sets of samples as well. The first main takeaway from this set of data is that both the glass transition temperature and the storage modulus at room temperature, which indicate thermal stability, and also it can give an indication of structural properties at room temperature as well. All of these qualities and characteristics increase with the post-curing procedure, and the fractional conversion of monomers also increased with this post-curing procedure as well. This proves the necessity of a post-curing procedure, and it also shows how high these properties can potentially get with a glass transition temperature around 139 to 144 degrees Celsius for all of these systems, which is pretty decent. However, something that looks a little strange, and you might see it here, but if you haven't, I'll point it out, is in the as printed specimen of vinyl ester NVP resins, we see materials with two very distinct peaks on the loss modulus curve. And this often indicates that there are two phases that are present. And I've got this multiple times. It is not a fluke. It is something that happens. So what we believe is happening here can be explained using the conversion data that I've just highlighted within this row. The vinyl ester obtains a conversion of 30%, but the diluent is only reacted to an extent of 7%. If you recall the discussion we just had on reaction kinetics and reactivity ratios, this aligns pretty well with that. So we have our block copolymer that is mainly vinyl ester. However, 93% of the 93% of the NVP remains very much unreacted and unincorporated into the system. So the first highest TG phase here, or glass transition phase, is the bulk vinyl ester network that's formed. And this very low one is potentially, unreacted N-vinyl pyrrolidone within the system. When you apply the post-cure procedure, again, these values increase similar to the other ones. And now we see that the vinyl ester has reached 81% conversion and the diluent has reached 91% conversion. This indicates that the NVP monomers have homopolymerized to some extent. If you recall, again, the discussion I had previously on reactivity ratios, we know that vinyl ester monomers do not want to polymerize with NVP monomers. So it's more likely that they're homopolymerizing and they're entangled throughout the bulk network structure. And this argument can be further backed up by the degradation temperature that we see here that I've pointed out. If you take a look within the literature, and I've cited a source here, degradation of homopolymerized N-vinyl pyrrolidone occurs around 225, 250 degrees Celsius. And that is where this curve is beginning to taper off here. So it aligns well with this whole argument that we've been building in terms of this system of vinyl ester with NVP as a reactive diluent. Finally, evaluate the mechanical properties of printed vinyl ester thermosets for all of these systems. I show as printed and post-cured. Again, these properties do all increase pretty well, flexural modulus and flexural strength when a post-curing procedure is applied. I also performed fracture toughness properties on fully post-cured specimen, and I'll get to those in a second. There is some interesting things to look at in this flexural data. So first, again, with the N-vinyl pyrrolidone system, we have a very high flexural modulus, much higher than either of the other two systems as printed. Again, this is because of the sufficient vinyl ester network that is formed at this point. And then after post-cure, the flexural strength of this material is greatly increased, likely due to the homopolymers of NVP that have formed within those systems, reinforcing the overall polymer network. Both paramethylstyrene and acrylomorphin after post-cure do obtain pretty good flexural modulus and strength as well. Combined with the high glass transition temperature, these do produce overall pretty decent materials. Something, again, another point of interest is within the acrylomorphin system, you do have a pretty low, relatively low compared to the other two flexural modulus here. And why might that be occurring? Well, if we recall that acrylomorphin has an alternating copolymer network, it means that the vinyl ester monomers are pretty evenly spaced out. And this creates larger distances between cross-linking sites. If you think of it like a fisher's net, if you have large spaces between the knots in your rope, it's a pretty ductile network that you've formed. And it's the same case with polymeric materials as well. And this ductility lends itself well to the toughness of this material. So if we look over here at the toughness information, we see that acrylomorphin systems or vinyl ester systems containing acrylomorphin do obtain the highest fracture toughness and plane strain energy release rate values as measured by single edge notched samples that I show up here for each of my systems. This is very different than what we see again with NVP because vinyl ester oligomers really want to just homopolymerize with themselves. There's much less distance between those cross-linking sites. You have a fisher's net or a network where there's very little distance between the knots there. So it's much less ductile and you have a higher stiffness to that overall material. However, if we look at the fracture toughness properties, these systems are still not brittle. And the answer for why that is, again, might lie in the fact that it has thermoplastic or NVP homopolymer reinforcements throughout it. Overall, though, again, all these systems do obtain good thermal mechanical properties and decent fracture toughness properties as well, at least all over 0.4 megapascals times meters to the 1/2, that should be. So to conclude this work here, there is a clear influence of reactive diluent monomer on the processability, copolymerization kinetics, and material properties of printed vinyl ester thermosets. Overall, our lab did decide to continue with paramethylstyrene to continue working with for the reasons that I have listed here because I am out of time. We've made some base resins that we use within the lab for study on additive manufacturing. Thank you so much for listening. And I guess if there are questions, I can answer them by email. Thank you.